Okay, hi. Hi everyone. Welcome back. So I'll start with a reminder of what we're going to do today, what we did last time, and when we're going, and then I'll give you 2 minutes for questions and we'll continue where we stopped there. So what we were talking about, we were making our ways towards an NMR quantum computer system, right? Okay. And you know, this path will lead us to introduce some concepts from quantum optics, and we started discussing a classical magnetic moment. Okay, this is what we did last time. So we're going to continue our classical magnetic moment, okay, our description. Then we're going to see how this classical magnetic moment basically behaves the same as a quantized system. Okay, we're going to see the quantum version of this. Okay. And then what we're going to do is we're going to see how these interact with light. So we're going to take the classical magnetic moment, we're going to add some fields to it, see how we can manipulate the classical system. Then we will see that it behaves just like the quantum system. Then we will see how a general two-level quantized system behaves with a classical field, and that will be enough for us to start describing an NMR system. And then we'll build an NMR quantum computer, and then you can see how these things kind of play out. Okay, so this is what we're continuing now, our classical magnetic moment. And what I wanted to show you are two specific things about this classical magnetic moment. So we're going to be seeing two classical things which are the equivalent of the quantum phenomena. One is Rabi oscillations, and two, something that is called rapid adiabatic passage, okay, or in the quantum version, Landau-Zener transitions. And what we saw last time is basically I introduced to you the equations of motion for a classical magnetic moment, and we saw that the time derivative of the angular momentum is just gamma times the angular momentum cross B, where B was the magnetic field. And we saw that the solution is basically an oscillation at the Larmor frequency, which was defined as minus gamma B. Okay. So are there any questions about this, or I can continue to... The next step we're going to do is we're going to go into the rotating frames, and then we're going to apply classical AC fields to see how this gets manipulated. So are there any questions about what we did last time? No. Okay, so let's continue. So now what we're going to do, so we apply this, this field, and it's a DC field, okay, B, and now we're going to go into the rotating frame. So go into rotating frame of this magnetic moment. And we're going to go into a frame, basically to go into a rotating frame. You've seen this in classical mechanics course. You define some vector omega. This is the vector that defines the frame that we're rotating into. Okay. And then some physical A dot will just be omega cross A. Okay, so this should be familiar to you. And then in the lab frame, A dot will just equal A dot prime. Prime is the rotating frame. Okay, so prime will symbolize the rotating frame plus omega cross A. And if we apply this towards our angular momentum, then L dot prime, the angular momentum in the rotating frame, is just going to equal L, or L dot, sorry, the angular momentum in the lab frame minus omega cross L, which is just going to be gamma L. I'm just plugging what we had before into this, cross B plus omega over gamma. And now the choice for the Larmor frequency is very clear. Okay? So if we choose omega to be minus gamma B, and this just comes out to be the Larmor frequency B over the size of B. This is Larmor frequency. Okay, so basically we're going into the frame of the Larmor frequency, and if we choose this, we get what we expect, and that is that L dot prime equals 0. Okay.
Shay?
Yes?
The last thing you wrote on the far right is just on the border of the camera, so
okay.
It's hard to see.
I'll rewrite it. Just a second. I'll rewrite it. It's here. Omega equals minus. Wait, erase and rewrite it. So this is the Larmor frequency. This is B, the magnetic field, over the size of B. Okay?
Great, thank you.
And then we get the time derivative of the angular momentum in the rotating frame is now 0. Now what we did here is pretty trivial. Remember, we had our magnetic moment. We apply a magnetic field. What happens is, suppose the magnetic field is in the z direction. Our magnetic moment starts rotating at the Larmor frequency in this magnetic field. This is the lab frame. And now all we're doing is we're going into the frame that is rotating at this frequency. So what is happening is that this magnetic moment just seems static. It just stands there and points in some static direction in space. And this is exactly what we did here. Now the next step that we're going to do is we're going to add an alternating field, a rotating magnetic field in the lab frame. And we're going to see how that affects our magnetic moment. Okay? So maybe we'll do this on a new board. So now we add a time-dependent magnetic field. And now we're going to assume that this magnetic field is a rotating field. Okay. In real system, it's going to be a linear field, but a linear field is just a superposition or a combination of a field that is rotating in one direction and in the other direction. But for the simplification of this example, we're going to assume that it's rotating. Okay? So we're going to assume a rotating magnetic field. Maybe I'll put here for now. So let's write the field. So B as function of time is going to be some B rod. This is a number. The amplitude of the rotating field times cosine omega LT. So it's going to be rotating at the Larmor frequency plus, sorry, I have the sign minus here, minus sine omega LT y plus our static magnetic field in the z direction. Okay, so this is our magnetic field. So we have a component in the z direction. This is going to be BZ. This is in the lab frame. And a rotating field with an amplitude B rotation. So this is the field that's being applied to our magnetic moment. And now let's write what this field looks like inside the rotating frame. So B of t inside the rotating frame is going to be our original B of t in the lab frame minus omega L over gamma z. And if we write this in terms of the coordinates in our rotating frame, this is just going to be B0, sorry, not B0, B rotation, B rot, this number here, x prime. So, what are going to be the dynamics inside the rotating frame? Anyone? What will the dynamics in the rotating frame look like? There, this is the equation. This is the field. What happens when we apply a field to a magnetic moment? Anyone?
To a curve, not curve, cycle.
It starts to rotate.
Rotate.
Okay, it will start to rotate. In the lab frame, we applied a magnetic field in the z direction, and we saw rotation around the z-axis. Now, in our rotating frame, inside our rotating frame, the combination of our magnetic field in the b direction, in the z direction, and the AC field in the lab frame is causing an effective constant field in the z direction. So what's going to happen now? Our magnetic moment is going to start rotating around which axis?
The X one.
The x-axis. Okay, so it's going to rotate around the x-axis. Okay. In the lab frame, it's going to be doing some spirals. Okay, so it's going to be rotating fast at the Larmor frequency, and it's also going to be going from this direction somehow to this direction. Okay, my hand may not be the best animation. You can, look online for better animations, but something like that. But if we just look in the rotating frame, it looks like it's just flipping around. And this rotation around the x-axis, this is the equivalent, this is the classical equivalent of Rabi oscillations. Okay, your magnetic moment is basically going from pointing up to pointing down and back and so on and so forth. Okay, so we're going to be, so this application of an AC field allows us to rotate around a certain axis, the x-axis in this case, the magnetization of our spin, of our magnetic moment. Now, if you want to go over these calculations and things, please read Chapter 2 in Charles Slichter, Principles of Magnetic Resonance. I mentioned that book in the last class, but I'm going to mention it again. But now I want to explain a little bit about these dynamics that we're seeing here. Okay? So this causes these oscillations, which I said are the classical equivalent of Rabi oscillations, and the frequency of these rotations is just going to be omega r, and this is just going to be gamma b rotation. So the amplitude of our AC field defines the frequency of the oscillation of the magnetic moment. Okay? And if we want to take our magnetization and flip it by 180 degrees, this is a pi rotation. This is something that would be equivalent to a pi pulse. Okay, later we'll equate this, as you will see, we will later equate this and think of this a little bit like a qubit, but this is still completely classical. The flipping of the magnetization is basically equivalent. So a pi rotation, okay, so you can do a pi rotation by basically applying this field for how long? Anyone? This is your frequency. I want to get a pi rotation, flip the magnetization.
Half the period.
Half a period, which is, yeah, pi over omega r. Okay? This will flip it. Another thing you can do is you don't have to flip it completely. You can do half a rotation. So you can do a pi half rotation. And the pi half rotation will take our magnetization and put it on the equator. So suppose that our magnetic moment starts like this. We apply a big DC field like this. So our magnetization relaxes up in the z direction. And now we apply our AC field to put it in plane. What happens now to the magnetic moment? It just sits there. Okay. In the lab frame, it's rotating at the Larmor frequency. Okay? So this gives us a way to rotate our magnetization around the x-axis. Can we rotate the magnetization around the z-axis? Anyone knows how to do that? In the rotating frame, how do we rotate around the z-axis? I'll write the question up here while you're thinking. How to rotate around z-axis. I'll put z prime here.
But in the rotating flame, right?
Repeat that, I couldn't hear.
You're asking how to rotate in the rotating flame.
In the rotating frame, yes. In the rotating frame, how do I rotate around the z-axis? Let's call this a z. Think of it as a z operation. All right, so I want to know how to do a z operation, but it's still a classical magnetic moment. I'll give you the answer. Well, there are two answers.
Can you rotate for... Can I try?
Yeah, go ahead.
If you can rotate along the x-axis, so you can rotate along the y-axis, and you can rotate both of them one after the other, which should give something like a z-axis rotation.
Yeah, you can do a combination of those. You need to change the phases. I'll expand on that a little bit more. Anyone has any other ideas? There are two more methods to do it. Two more ways to do it. One way, you can apply that's right, additional z field, magnetic field in the z direction for a while. So you add some magnetic field, and now if you add a little bit of magnetic field, now your spin, your magnetic moment is processing a little faster. So it's supposed to be static like this in the rotating frame, but you added some B field. So now it's drifting away from your frame, because in the lab frame, this is the Larmor frequency, but it's actually rotating slightly faster. So it's acquiring phase as function of time. Okay, and the Z operation is exactly acquiring extra phase. Also in quantum computation, acquiring phase is a Z operation. This is why I'm connecting the two, okay? So you add a little bit of Z field. a little bit of B field. But what if you don't have extra B field to add? Well, another thing you can do is wait. Or basically change frame. What you can do is you can trick the clock of your experiment. Okay? When you do an experiment, you're timekeeping. You have some atomic clock or some oscillator that is very accurate in keeping time on a time scale which is much more accurate than the time scales of your experiment. You have to have that. And this clock that's keeping time, it is the clock that's telling you which frame you're in. But now, let's suppose that our brightest student, who's our brightest student? Who wants to be the brightest student? Raise your hand. Anyone? No one's raising their hand. I can see someone smiling in the middle. Your pictures are very tiny, but someone in the middle is smiling. So you're going to be the brightest student. Okay? So that brightest student, what's your name? Yellow shirt. Yeah, yellow shirt. Sorry.
No.
Noga. Okay, you're going to be the brightest student. Okay? And what you do is you go to this clock, and your lab mate, he's doing this experiment. Who's your lab mate? Pick a lab mate. Someone around you. Pick a lab mate.
Oded.
Oded. Okay, all right. So, yeah, all right, Oded. So Oded is doing this experiment, okay? And he has this atomic clock that's keeping time perfectly, and it's in the Larmor frequency, so he's looking at his magnetic moment, and it's sitting there perfectly still. But then Noga, right, she pranks Oded. And she comes along and she changes the time frame for a moment. And that just causes this phase shift. Nothing happened in the experimental apparatus, in terms of the magnetic moment itself. All that's happened is you changed the way that Oded counts time for a moment. So you're changing his clock so he's counting time, let's say, slower. And then the magnetic moment is just drifting, and then you bring it back. And he hasn't noticed. But if he were to do tomography on this thing or measure the magnetic moment, he would see that it drifted. Okay? He wouldn't be able to distinguish if someone added a Z field for a moment or that you tricked him and you changed the clock for a while. All those create some phase accumulation. Okay? So those are two ways to do it. The third way is what, hang on, I'll look on the screen here. Daniel said before. Okay? What Daniel said before, you can do rotation around the X and a rotation around the Y, or two rotations with different phases. Okay? And let me write this explicitly as phase of rotation. Okay? The calculation that I showed you before, the equation that I wrote before on the other board, shows how you can do a rotation around the x-axis. But if I write again the magnetic field in the lab frame, and now I'm going to write it a little different. I'm going to add a phase, degree of freedom. So we have cosine omega LT, but now I'm going to allow a phase. Okay? Now the phase is just the phase of a sine wave. You have a classical, the phase of this rotating magnetic field. So you have a magnetic field that's rotating, and it has some phase. Okay, so we're going to add this phase over here, and here we had minus sine omega L t plus phi y. Okay, and we had bz over here, bz. Z. And you can clearly see that if I set phi to be pi over 2, then my rotation's around the y-axis. And basically whatever phi I choose is the angle of the axis that I'm going to be rotating around. So with this field, basically what we've established is full control over this magnetic moment in the rotating frame. We can rotate around any horizontal axis that we want, and we can rotate around the z-axis. And all this we're doing by driving on resonance. And now let me ask a question. What happens if we drive off resonant? So now our Larmor frequency is going to be, our driving frequency is going to be different than the Larmor frequency. So we're going to add a slight detuning. So off resonant driving. So omega drive is different than omega Larmor. Anyone? I'm going to pick on the black squares because I can read their names from here. Amot.
Yes.
Yeah. What happens if I drive off resonant? Do you know? Good guess. All right. Anyone else? No. Okay. So what would happen if I was driving on resonance, but somebody, our previous trickster, changed the magnetic field without us knowing? Noga was the previous trickster. So she tricked us again. She tricked Oded, and she changed the magnetic field. What happens then? We just discussed the case. What happens?
It drifts.
It drifts. We have a drift of the phase. But who says what is the Larmor frequency? Right? Adding a B field is exactly equivalent to driving off resonance. Right? The B field defines our Larmor frequency. Okay? But, so this is Larmor frequency. I can drive off resonant, but it just means that I'm driving at a frequency that does not correspond to the Larmor frequency of the B field. Okay? So I could be driving at this frequency thinking that this is the magnetic field, but actually someone tricked me and this is the magnetic field. So this is the real Larmor frequency. The y-axis here is frequency. Okay? So adding an extra B field is equivalent to driving off resonance. And we know what happens if we add an extra B field. We get extra phase accumulation. Okay, we get extra phase accumulation. We have an extra B field. And if we draw this, it looks like this. So in the rotating frame, we have this extra field. So we have BZ prime. This is the extra field that our trickster Noga added. Okay? And this is B rotation, our AC field. Okay? And then we get an effective B prime. So in the rotating field, we have an effective field, which is basically B rot squared plus BZ prime squared. What happens to the oscillations is that they're going to be now much faster. The rotation, our rotation is going to be around our new effective field, B rotation prime. Our effective field is going to be bigger. So now our rotations are with frequency omega prime, which is omega drive minus omega Larmor frequency squared plus our Rabi frequency squared. So we're getting faster rotations. But these faster rotations are now around a different axis. Okay, so when we were driving on resonance, this is on resonance. If we started over here, we had rotations. This is a bad drawing. Okay, maybe I'll do it with my hands. I'm bad at drawing. Okay, so on resonance, we had rotations like this around the x-axis. Now when we're off resonance, we're now no longer driving around the x-axis, around some other tilted axis. So our rotation is going to be something like this. So suppose that our new axis is now 45 degrees. If this and this are equal, then our rotation is going to be something like this. It's going to be faster, but it's going to be doing smaller circles of the magnetization. And in the case where, so on resonance, it's something like this around the x-axis. Off resonant, so we're going to be slightly off resonant. I'll try to draw this. So this is our effective axis, so you're going to have rotations of the magnetization like this. And highly off resonance, meaning that our BZ field is much larger than B rot, then our axis is our rotation axis is basically almost parallel to the z-axis, but our rotation frequency is going to be very, very large. So we're going to get very, very fast, but tiny oscillations like this, until we're so far off resonant that the oscillations are basically kind of static right up there. Are those dynamics understood? Anyone?
It's not quite understood what happens in the limit, which we don't physically have, but it's still interesting though.
In the limit where the B field is very large? You actually do have that limit, because remember, this is a detuning, right? So think about, your Larmor frequency may be, I don't know, 100 megahertz or something, and you can apply your actual driving field at, let's say, almost DC, right? And then if you actually applied it at DC, then your detuning is enormous. Basically, you have, it's just like an added DC field. Okay? So if you have a very, very large detuning, you're highly off resonant. You're not doing anything basically to the magnetic moment. If you think about the AC field as something that can drive power, and on resonant, it's going to be flipping the magnetization. As you go off resonant, your effect is getting smaller and smaller. Okay? So you're coupling the most energy when you're on resonance, but as you go off resonance, you're getting less and less in. Okay? So your oscillations are becoming faster and faster and faster, but the solid angle, let's say, that's being acquired here is getting smaller and smaller and smaller. Okay? So if you're far detuned enough, sorry, ask again?
I thank you, because I understood what you said.
Oh, okay. All right. Yeah, so really far off resonance, you would just be basically static like this. Okay? Now, let's see how this comes into play, because it brings in something interesting, and this is what I told you that I'll get to, something that's called rapid adiabatic passage. Okay, so if you understood these dynamics, then I can explain what is rapid adiabatic passage, and it's a nice example of this. And try to imagine the following situation, where you have a bunch of these magnetic moments. So you have many of them, and you apply a B field. But the B field is completely inhomogeneous. So you have loads of magnetic moments over here, and you apply some B field, but it's inhomogeneous. So each magnetic moment sees a slightly different magnetic field. Now, if I try to do a rotation that flips the magnetization, what's going to happen? Someone who has not talked yet. Aviad, You there?
Yes,
All right, what's going to happen?
I'm here. Yeah. Can you repeat the question?
Yeah, I said what's going to happen if I do a pulse for pi over omega Rabi, corresponding to what I think is the B field, but B is inhomogeneous. What's going to happen to the magnetic moments?
Depend on how they see the B field. Like if there is someone which is exactly the same,
It's non-homogeneous. So on average, it's this thing. But over here, it's going to be different than over here, different than over here, different than over here.
So they spin in other direction.
They will rotate at a different frequency. Okay,
Yeah.
Remember the dynamics. It will be off-resonant driving. So for some spins, so for some magnetic moments, it will be on resonance. So they'll be doing this thing. But others will not be rotating like this. They'll be rotating faster and around some different axis.
Yeah.
Okay? But suppose that we actually want to go and flip all the spins. We apply this B field. Okay? And everything relaxes, so all our magnetic moments are going to be aligned with the B field after everything relaxes, and we want all of them to flip exactly by 180 degrees. So what we want to do is a robust pi operation, let's call this. We don't care about the time. It can take us long, but we want to do this robust pi operation. And by using this thing called rapid adiabatic passage, we're going to see how it's done. And basically, you already have the answer, because I showed you what off-resonance driving looks like. Okay? So think about the situation that I just described. Okay? And what's going to happen is we're going to start our drive highly off-resonant. So we have a drive highly off-resonant, AC field, and this is frequency axis. And then we're going to scan right through resonance, or right through where we think is resonance, highly detuned from one side all the way to highly detuned in the other side. Okay? And the scanning is going to be rapid with respect to the environment. Okay, we haven't talked yet about the environment, but if we apply a B field, eventually all our magnetic moments are going to align with the B field due to relaxation, energy relaxation. We'll talk about that after we're done with this. But now that everything is relaxed, we want to do this rotation. But if we do it much slower than the environment is flipping our magnetic moments backwards and forwards, then that's a little silly. So we want to do it faster, fast with respect to the environment. But we're going to be doing it adiabatic. Adiabatic, which means slow, with respect to the Larmor frequency. Okay? Meaning that omega dot, the rate at which we're going to be changing our driving frequency, so omega drive dot, is going to be much smaller than the Larmor frequency. Okay, so these two are kind of contradicting. So rapid adiabatic sounds a little silly. They cancel each other, in a sense. But it's rapid with respect to the environment, but slow with respect to the Larmor frequency. And basically what happens, each spin, we don't care that each magnetic moment sees a different field. Okay, so think about, this is our frequency axis, and we have many magnetic moments, and these are their respective Larmor frequencies. They're spread all around here. due to our inhomogeneous field in this example. And now we go highly off resonant. This is omega drive. And when we're highly off resonant, nothing is happening. So all the spins are very rapidly rotating like this around the z-axis. So effectively they're static like this. And now we start scanning omega drive very slowly. And what's going to happen is, so this rotation is going to start turning slowly into this rotation, and basically these slow rotations are going to cause the magnetic moment to follow our effective field. Okay? And what I'm describing here is the dynamics of each of these. So each of these magnetic moments will pass through this point at a different time in the scan, but they will also all be doing this. And at the end, when we go to frequencies which are far away, again, they'll be stuck like this. Okay? So we're taking all these magnetic moments and we're robustly flipping them by 180 degrees. Okay? Now, I'm not going to go through the proof of this, but if you want the proof, look in page 23 of the Charles Slichter book. Now, I'm going to be doing this several times throughout the course, not giving proofs or leaving out stuff that you can find in books just to make you open the books. Okay? So you can look at the proof of this in this book over here.
Just to make sure that I understand,
Yes.
Once you finish the scan, you have all the moments pointing on the same direction, and then you do your pi operation?
No, that is the pi operation. You started here,
okay.
right? And as you're scanning, all these magnetic moments are now flipping. Sorry. They're flipping, and then they end up like this.
And once you have done it, you can do another operations without the scan, right? Because
you can do whatever you want, but note that any operation that you do with just AC field driving, if you just drive on resonance over here, you can also try to do this pi rotation by driving over here, but then you'll be flipping anyone that's around here by 180 degrees, but all these will be flipping at a different angle, right? They'll be rotating faster and at a different angle, okay? So they won't exactly flip. What this does is creates a robust way to flip the magnetization. Okay?
Can I have a question?
Yes.
What is the cause of the difference of the frequency of the different particles?
Well, each of them sees a different Larmor frequency. If we move back to this board over here, remember, I didn't look at these dynamics for nothing, right? When you're driving highly off resonant, your frequency is much faster, and it looks effectively as if you have an additional Z field. Okay, so these are the dynamics. So when you're on resonance, you have this, but when you're highly off resonant, it looks like this. So we start highly off resonant.
My question was different, I think.
Oh, okay. So ask again.
When we had a lot of particles,
yeah,
and all of the Larmor frequency of them are a little bit different. You showed on the graph, right?
Oh, I drew them differently because I assumed that the B field is, for this example, what I did is I assumed that the B field is inhomogeneous. So I forced the problem into the case where you have that each magnetic moment sees a different field. This is actually a realistic case in NMR. Every magnetic moment, every spin, really, in NMR, it spins, sees a slightly different magnetic field. Okay?
Okay, thank you.
So you can deal with these in different ways. We will see that, but here, just to show this, I assumed this case also. So this comes from the inhomogeneity. Okay. So are there any other questions about this thing? Now, this classical picture of rapid adiabatic passage, if anyone knows, it connects to the Landau-Zener transitions of a two-level system, and we'll see later a two-level system and how that plays out there. Okay, so at this point, at this point we're done with our classical magnetic moment in a classical field, and what we're going to do now is we're going to see how a quantum spin behaves in a classical magnetic field, and basically we're going to see that they behave the same, so they have the same dynamics. Okay?
Can I ask a question?
Yes, please do.
What happens if the relaxation time defines a frequency which is very close to the other frequency, the Larmor frequency, and so it's difficult to find something in between that will not have some boundary effects of being too close to one of the limits or both of them.
Yeah, that's correct. So basically you want to, if you're thinking about an NMR or an experiment, you want to put a high enough Z field such that your Larmor frequency is fast enough so that it is much, much faster than all other timescales. So usually you have a relaxation timescale. In NMR it can be milliseconds to even seconds. That could be the energy relaxation scale, depending on the density of the solution. And if you remember, last lesson I even wrote down on the board, NMR is usually played out in fields of around 10 Tesla, 11 Tesla, so your Larmor frequency is hundreds of megahertz. Now, you can even do this with hundreds of kilohertz. Even that is enough to do many, many operations to, let's, for example, measure the relaxation times, which we will see after we take a short break. Or, I don't know, we'll see if we get to that. We'll have to do the quantum spin first. But,
Thank you very much.
Okay. Any other questions?
Yes, I have another one. If we, in this experiment, we start with a omega D frequency, which is much smaller than omega Larmor frequency, and then you go away to the frequency which is higher than Larmor frequency, right?
Yeah.
In the end.
That's what I drew on the board. Yeah.
So in the middle, you pass the Larmor frequency, which causes the spin rotating of pi. Like it's not going to stay small in the middle.
Oh no. So maybe you misunderstood my explanation. Maybe you misunderstood my explanation. Let me. Okay, your question shows me that you misunderstood my explanation, so I will explain again. Okay, I probably wasn't clear enough. So at this point, what is happening is we have our magnetic moments, and they're rotating very fast around this axis. We're okay. Now, we're gonna move slowly with the frequency. So as we move over here, what's going to happen is that our effective field now, this is our axis, now our effective field is over here. So before our rotation was here, but now we move just a tiny bit. So it's not that our rotation is going to be like this. Our rotation is going to get dragged along. So now our rotation is going to be like that.
All right.
Okay? And as you move along, now your rotation is going to be like that. And so when you get to this point, your rotation is going to be like that. You understand? So when you're in the middle, your rotation axis is the x-axis, but the magnetization is also aligned with the x-axis. Does that clear up my explanation?
Yes, thank you.
Okay. All right. Any other questions? Okay, so let's take a 10-minute break, and then we'll continue with dynamics of a quantum spin.